Thank you very much. I'm Alexandre Sirois-Vigneux, if you want to try to pronounce it. You win $1,000 if you get it right the first time. I'm a senior 3D software developer at SideFX, and and I'm here to talk to you about the new MPM solver inside of Houdini 20.5. You might know a little bit about this solver just because the very first talk that we had this week was by Anse, one of our interns that should be in the crowd at the moment. She's right here. And her talk was super cool about what she'd done with the landslide scene and also a lava scene. So just to give you like a quick overview, in case you know nothing about MPM, MPM is like this flip solver that is extended to do solid mechanics. So think about everything that you love or hate about flip. It's kind of similar with MPM, but now you can have like a ball of snow falling, you can have some soil, and even some very stiff material like metal and concrete. But yeah, you can even have interaction, like those materials can interact together, so it's this cool new thing where you can do a lot. But the one thing with MPM is the algorithm itself is kind of slow, like on itself. It's like back in the days when people were talking about doing ray tracing, other people were like, man, you're crazy, you're never gonna do ray tracing, it doesn't make any sense. And now we do like real-time path tracing. So MPM is the same thing. You have to leverage the hardware as much as possible. So this is why our implementation is all done in OpenCL, because we want it to be running on GPU as much as possible, just to make it more production ready and useful for you. So, in case you're not aware, we have a masterclass that is live at the moment on Vimeo. It's 3 hours long, so just get ready for it. You're gonna hear my bad English for a while if you look at it. But there's a ton of information, and it should get you up to speed with the solver in no time. And if you like hands-on approach, you're gonna appreciate this one because all of those images that you see are scenes that are part of the masterclass, and I'm just breaking down all the different steps that you need to recreate all of these scenes. The IP file and the assets are all available with the masterclass, so just, yeah, you can recreate them on your side for sure. And just to give you a little more context, if you want, you can scan the QR code to access the masterclass. And apart from that, we start with some theory. After that, we jump in Houdini and we look at the nodes and the feature that we have available to us. And we finish with those breakdowns of the more advanced scenes. And at the very end, there's some tips and tricks to how to troubleshoot your scenes, how to, like the little subtleties about MPM, the gotchas and things like that, that you need to know to be efficient with this new solver. And from the people that have watched the masterclass, they say it's great, exciting, enjoyable, and amazing. And best thing, we paid them very little to say so. So I would trust that for sure. Okay, it's demo time because I'm very brave. So we're gonna go in Houdini and look at what we have available to us. Okay, so yeah, let's start with a geometry node. And in there, you can type MPM configure, and you get all of those cool recipes. So I personally never lay down the MPM nodes myself. I always start with the recipe because it connects everything for you. Most of them are also example scenes where you can learn a lot of feature of the solver. But the main one I always use when I want to start from scratch is this MPM configure, which is very simple. So it's oh yeah, so the first time that you're going to use MPM, there's some cooking happening because it has to compile all of those kernels for your hardware. So every time that you do something new, it will have, you'll have this hit in performance. At the bottom it says compiling OpenCL kernel, but this is all good. After that, after it's done once, it's gonna be fast for the rest of your cooks. Okay, so what we have here is just this simple ball of snow. If we play this, it will compile another kernel for sure. So I'm realizing that we might have some hits in performance for this presentation because all of these are not cooked on this machine. I don't know what to do other than waiting. Like, I'm sure it's gonna get there in 3 seconds. Almost. Yeah. That's the reason why I was saying, yeah, live demo, you know. My God. Applying collision. Man, you're doing so many things for this demo. Just do the bare minimum and get this going. Okay, so I might not, like I'm still going to run with this example, but I might not do all of the things that I wanted to show you just because there might have other things that we'll need to cook. But okay, we have this very basic example. When you select all of these nodes, this is the sub nodes that you have for MPM. The one weird thing about this set of nodes is like if you go to view and you display show dependency link for selected nodes, you're going to see that when you select this NPM container, you have a link going from the container to those the source, the NPM source and the NPM collider. And the reason for that is those two nodes, they need to be aware of the global resolution of the sim to be configured properly. So you either have the option to use this parameter on top, like this NPM container thing, where you just like plug this in, or you can have an explicit connection. So if you select those two nodes and you just use this input, you can connect it like that. But yeah, it will very quickly make your node network look like a noodle mess. So I personally don't really use that. But if you prefer to have explicit connection, you can do that. So this is the first weirdness about NPM. But the cool thing is that it makes your tree very like semantically. It tells a lot by just looking at the tree because you have all of your sources on one branch, all of your colliders on one branch, and it's not just like coming from a single wire. After that, if we look at each node individually, the main things that you need to know about the NPM source, the emission type. So at the moment, it's just emitting once. So this is like the basic stuff. If you want to fill like a container with some material, you can use continuous emission. After that, for the type of like point scattering, at the moment, it's filling a volume here, but you can do surface. So it's just going to do like the outer shell of the geometry. You can even do some relaxed iteration just to have like proper coverage. And down here, you have your material tab. And personally, I would just start with the preset. So just pick a preset that is close to what you're trying to simulate. And after that, you can spend some time fiddling with the parameters here. But yeah, for now, we can just pick rubber. And now if we simulate, of course, it's going to compile another kernel. But this should be quicker. So the very first time you're going to play with NPM, it's going to be like this, like in terms of compiling the kernels. But yeah, as it's being compiled once, you won't have to run to this again. So now we have this cool new look. For the NPM collider, the main thing that you have to know about is this collision type. So at the moment, this is set to static. So this is our basic collider that doesn't move. But you can have animated collider for sure. And this animated rigid type that I just selected is the most important one. So if we just create a transform node, I'm just going to add some rotation to it. Okay, so now we have this turning like this. If I connect that to the NPM collider, it picks up the animation. But more than that, if you look at the wireframe, you can see that the wireframe, like the bounding box, is moving with the collider because it's being built once, and then after that, there's only new transformations that are being fed to the NPM solver, and the transformations are being interpolated. So this is much more accurate than doing the other mode, which is the animated deforming. With the animated deforming, you can see like the VDB is being rebuilt on every single frame. And it's just less accurate, and it also takes more time to rebuild the VDB on each frame. So whenever you have like a rigid transformation, use the other mode. And if you have like deforming character, for sure, you have to go with this guy. Now I'm afraid, like, I'm wondering if this is going to compile or not. If I just, okay, no, it's working. Cool. And I can probably revert that to something more interesting. Okay, so we have our collision now. For the NPM container, as I said, it's setting up the resolution, so particle separation here, and also the start frame. So those are the two main reasons why they need to be, like those two nodes need to be aware of this one. And after that, you can close the boundaries just as an optimization. You don't need to because NPM is a sparse solver, but if you want, you can restrict the space and say like, okay, I don't want things to escape this domain. So now we have the particles that are being trapped by this blue box. And I'm just going to remove the animation. Okay, and for the solver itself, again, I'm just going over like the main features real quick. A lot of people are super scared by this maximum number of substeps. They are terrified by that, and I'm going to like help you to chill more about that. So if I go to Inspector, Geometry Spreadsheet, okay, you see here in the spreadsheet you have substep count. So if you just do one frame of simulation, it tells you, okay, it took 19 substeps to simulate. So even if you have this max to 10,000, the reason why we have this capped at 10,000 is if you do very stiff material, like if you do concrete or metal, it's going to increase the number of substeps quite a bit, like maybe 500, 1,000, 2,000, depending on the stiffness of the material, it will go very high. But for things like snow, soil, those materials that are more compressible and not as stiff, it's not a problem. But yeah, for example, we can see like if I change the volume, the material type for concrete, and we simulate one frame, okay, now we're at 500 substeps. And it's still going pretty fast because everything is working, it's running in a tight loop on the GPU. So there's no back and forth between the host and the GPU, but still it increased the time for sure. So you can always, as you're working with MPM and you're trying to optimize your scene, always keep an eye on this value, just to have an idea of why things are being slow. And you can try to reduce this you can try to reduce this value here, like this maximum substep count, but just keep in mind that if you reduce it too much, it might induce some instability in the sim. It might not work as well. Then for the rest, okay, we have some forces, ground plane. This is more usual. Here you can visualize the different things, like the container, the collider, the ground plane. And for the outputs, we have this deformation gradient attribute. This is super useful. I'm just going to create a new So now if I export this attribute, so by default it's off because it's a 3x3 matrix, so it's pretty heavy. And now I'm just going to create a point triangle. And I'm going to this deformation gradient is giving you like the local transformation on each point. So what you can do is if you don't need scale, shear, and rotation, you can try to just extract the orientation from it. So I can just do orient is equal to quaternion of this. And then, so this converts a 9-float attribute into just a 4-float attribute, so much lighter. So if you want to cache this information on disk and you don't need the full transformation matrix, you can do that. And in this case, we can visualize also the frame of each particles. And if I run this, not really sure why we're not seeing. Okay. Sounds good. Yeah. Oh yeah, okay, that's true. Perfect. So if we run this sim, 2 more frames. And then we look. Oops, sorry. This, okay. So you can see that without doing any effort, we have this orientation information. So you see like the particle falling, you see they are tumbling, they are rolling. So all of this information, usually with other solver, you would need to calculate or approximate how the particle would be orienting as they are falling. But with MPM, it's just out of the box with this attribute. And the other important attribute that you should know about is this plastic compression and stretching, JP. So J stands for the determinant of matrix. So in this case, this is the determinant of the plastic component of the deformation gradient. So it's quite long, but the only thing that you need to know about this is, like if we visualize it in this case, So here we're visualizing this JP attribute. It's going to detect those fractures. So as things are breaking, so they are plastically deformed because they are not going to recover from this fracture. They are going to be picked up, like this information is going to be stored in this JP attribute. So you can very easily use this data to drive a secondary sim and have very cool debris emission and things like that. Okay, so I think that's all for this demo. Oh, and yeah, maybe one last thing. There's a dive target, so you can dive inside of this node, and you can put some pop nodes, vex node, OpenCL nodes if you want to have more control over the simulation. If you want to add some wind, some noise, you can do it here. Okay, back to the presentation. Okay, so now I'm going to talk about this little shot that I've done for this presentation. I was originally supposed to reuse the masterclass material for this presentation, but I thought it was way too sad, especially since you come from so far away, some of you. So I decided, okay, I'm going to force myself a little bit and do something new. And I tried to do something that is not related to MPM. Like naturally, when you think about MPM, you will never think about this kind of shot. But I wanted to show you how you can use MPM in more creative ways to do unusual effects, let's say. So this is the shot that I ended up doing. So it's like this galaxy where you have like some rocks, some stars, and some volumetric clouds. And now we're going to go through all the steps if you want to rebuild this with MPM. Okay, so first thing that I've done is look at some inspirational images from the Webb telescope. So I thought that those were pretty cool. And in particular, I really liked these three images, like those, the kind of structure that you see here, like this Webb spiral thing. I thought was really interesting. And the balance between those dense areas and this empty space. Also like the high frequency fiber look that you get in this image. And the very dense, sharp leading edge here. Those were all kind of elements that I wanted to put in the final shot. So after that, like every time you think about those large dynamical systems in space, you might think about Nbody Simulation. This is basically modeling the gravitational pull from one particle versus all the other particles in the system. So this is some Python code showing you like the basics, not the basics, but the core of the algorithm. So you have two nested loops because each particle needs to look at all the other particles. And basically you're storing a vector of the difference in position of those two particles. Then you compute the distance between the two particles. And you just aggregate and you gather acceleration and influence of particle J onto particle I. So you have a gravitational constant, the mass of J, because as the mass is bigger, it's going to pull more on the particle I. And then you use the vector to get like the proper direction to get from particle I to particle J. And all of this is being divided by the distance. So right away, you can see that you will run into some issues if you have two particles on top of each other. You're going to get a division by 0, or if you're not exactly at 0, it's going to have like a very strong acceleration. But we have a way to get around that in the OpenCL code. Another thing to keep in mind, here you have like two nested loops, and this big N here is, this is like the number of particles that you have in your system. So this is called quadratic scaling in algorithm complexity. And what this means is we're in trouble. Like this is not great at all because this is not going to scale gracefully. Like if you have 1 million particles, this is nothing for effects in general. But in this case, this inner body is going to loop like 1 trillion times for just 1 million particles. So even with good hardware, it's not going to scale to crazy amounts of particles. So we'll have to be smart and find a way to like up-res the simulation later after this main Nbody simulation. So this is the OpenCL code that we're going to use for the Nbody sim. And I'm just going to break it down so we see the connection between what we just saw and this. So first thing is just like our argument. So basically like the point attribute that we're fetching in. After that, this is just our condition to make sure that we run over valid data. Then we have this softening value. This is a value that we're adding to the difference in position between two particles, just to make sure that we never divide by 0. So we have like a little positive value to add there. Here we just initialize our temporary force variable that we will aggregate the acceleration in there. Then this part is exactly the same thing as we had in the previous slide. It's just formulated slightly differently for OpenCL, but trust me, the math is the same. And then this has nothing to do with NPM. It has nothing to do with Nbody Simulation. It's just what I would call like layout forces. So the kind of force that you put there to make sure that it looks kind of in the right place and it's doing the right thing. So here I'm just like flattening and making the galaxy spin. After that, I'm also doing some kind of terminal velocity for the particles that are going too far away from the center. I'm just slowing them down to make sure they don't pick up too much speed. And after that, we just store everything back into the force particle attribute. So all of these might look like terrible acts, but you have to remember that we all work in this industry where this kind of stuff is completely acceptable. So I'm just going to say, this is not the worst thing that physical accuracy I've seen recently, right? Okay, like, moving on. So if you take this OpenCL node and you drop it in a pop simulation, in a pop solver, you get this kind of look, which is interesting. But when I look at this, I see some missed opportunity, because like you see some big cluster of star or whatever that are slamming into each other without any interaction, without any reaction to each other. And since we cannot really scale to 4 billion stars, how can we add more interaction? How can we add more structure without scaling the number of particles too high? So for that reason, I decided to put physical accuracy in the trash again. And then we just add NPM to the mix, and we don't care about how realistic this modeling is. So this is the first test that I've done. It was just like an NPM logo written in text that I apply the Nbody algorithm to it. And right away, it looked pretty interesting to me, like it's creating some cool structure. Doesn't look like a galaxy yet, because this is using like the snow preset. But you know, there's something in there. And so after that, what I've done is try different presets. So I have like the soil preset, water, and sand preset, where I have this disk of particle where I'm just letting it run and see what kind of structure are emerging from those materials. And after that, by looking at this, I was like, okay, I'm just gonna merge everything together, and I should have more complexity, more cool structure. And this is what I've done after. And arguably, this one looks better. Like it takes a little bit of time to place itself and start to have a cool structure. But yeah, at some point, I would say that it has a better structure than all of the other simulations that I've done with isolated materials. So after that, the only thing you can do is like scale as much as you can. So I think this is 600,000 particles. So this is nothing for MPM, and this is nothing in general in FX. But for Nbody simulation, it's quite a bit because of the quadratic scaling. So since this is the maximum amount of particle we can go with, the only other way from there to close the gaps, because you see we have like a lot of like empty space, like a lot of empty pockets where nothing is happening. So one way to solve that is just to run the simulation longer and fold it on itself to just fill the gaps with data that has arrived a little earlier or a little after in the simulation. So this is what I've done here. So I'm just taking multiple slices of 100 frames, and I'm just compositing on top of each other to have more action going on, like something a little more dense visually. So now we're going to go inside of Houdini, and for this part, I'm not touching the mouse and the keyboard. We won't have to compile anything. So we start with a disk, and we scatter some points on it. Then we adjust the p-scale before we convert to a VDB. Then from this VDB, we fill this VDB with some points. So we're using the soil preset in this case. And then we assign a color just to identify the different materials. After that, we repeat the same process, but with different materials. So we have the water in the middle, and we have the sand on the right. And this is just using the default preset, so no number has been tweaked. I'm only changing the density for the soil, just to have more variation in there and have some particles that have more gravitational pull. And for the water and the sand, just the basic preset. Nothing changed there. After that, when we look at the point count, we have a little bit over 1 million. It might be a little bit for Nbody simulation. So I'm adding a fuse just to make sure that those things that are overlapping too much are reduced. So now with 600,000 particles, we should be good to run the Nbody simulation pretty easily. Then I'm setting some initial velocity for things to be spinning, and also some noise just to break up the initial condition of the simulation. And then after that, I'm multiplying the density of all those particles with some noise, just to add more breakup and more visual details. On the NPM solver, there's nothing going on, just the defaults. I'm removing the ground plane, of course, and I'm also adding some air drag because, of course, if you do a galaxy in space, you need that. And everything else is the default. And we have, of course, our Nbody node with the exact same code that I just showed you in the slide. It's in there in the dive target, so it's being processed on every frame and part of the MPM simulation. And after that, everything that you see below this point are the time shift that I'm like taking slices of 100 frames and I'm merging them all together to create the more complete galaxy simulation. Okay, so now we have this simulation at 600,000 points. So it's nothing to render. Like we cannot pass that to Karma. It's going to look like garbage. So how can we up-res this and get a little bit more details out of it? So the first test that I've done is just like I generate a new source with more points, and then I'm just like matching the velocity of the initial simulation, and I'm just trying to follow this main simulation. But also in this case, I was adding a force that was pulling the up-res sim toward the initial sim. So it was kind of shrinking those like this high resolution source was converging too much on the main sim, and we were losing a lot of details from it. So the other version, I remove this cohesion force. So there's just the velocity alignment here, and it looks a lot more fluffy, a lot more detailed. So I preferred this look. And then it's just a matter of, again, scaling up. So put as much particle as you can. So in this case, I think it's a little below 30 million particles. Not that much, but in this case, it's going to do it. So again, inside of Houdini, this is our up-res setup that we're going to look at. So we start with our previous MPM simulation, freeze the first frame, then we connect all the adjacent points. And here the idea, we're really trying to recreate like the fiber high frequency look that we had in our reference images. So first thing, I'm creating some connection between the points. Then I will store a normal attribute that is along each edges. Then I'm scattering some points. And now I will do something that I call the organic spread, which is like a jitter, but it's going to jitter along the plane that is perpendicular to each edge. And it's going to follow this ramp that we see top right. So the points that are closer to the ends of the edge are going to be jittered more. And what is close to the center of the edge is not going to be jittered at all. And when you do this, it's going to create this more organic look where you have those rounded pockets. I think I'm zooming in, yeah. So we have those rounded pockets of empty space, like where you had holes before. If you compare before, it was very like linear, very straight. Now it looks a little bit more organic. Then after that, we have this feedback loop where we just advec the points 10 times just to warp it a little bit in space and get something more natural. So we have those two noises with different frequency. And we get this kind of look. And it's getting closer to one of the reference I was aiming for. Before we had that, and now with this we have something more natural. Then after that, we will go inside of the pop sim. So we grab our MPM simulation on the right. And then in here, we have a very simple pop simulation. So the pop fluid here is just to avoid the points to completely like collapse onto each other. So we want them to like collide and preserve the space that they occupy. After that, we have this match vel, which is going to look up the velocity of the main MPM simulation and transfer that to the up-res particles. And the line right under it is about making the points not drift out too much of orbit. So we want to get the points like to be pulled a little bit toward the center to make sure that it's not going outside too fast. And after that, we just have a basic pop noise with some high frequency noise just to add a little bit of breakup and a little bit more details. And then right before caching, we scrap all of the attributes that we don't need, we remove the groups we don't need, and we cache that on disk, trying to get a little footprint. Okay, so the other branch that you see on the right, it's exactly the same thing. So the only difference is, like, I'm going to do some layering in the end for the render. So the first setup that we saw was for our dust cloud, and the second branch is for the rocks. So the only difference is the initial source that I'm jittering a little bit to get some differences in the two sources, but it's exactly the same thing in the end. So now we reach the rendering side of things. So here you can see like the final camera motion, and I have slowed down the high resolution sim of the galaxy just to get something that looks more massive, more interesting. Then we have the different layers. So this is the rock layer. So just like a very small basic model of a rock that is being instanced across all the points with different p-scale, different orientation. And also there's some little bit of animation in the rotation of the rocks to catch some glint and some specular highlights here and there. After that, there's the star layer, just emissive, small emissive spheres. And we have the cloud layer. And you can see we have some cool internal lighting because I'm using light instancing in this case. And yeah, it gives like very cool internal lighting in some places. Again, back in Houdini to know how we've done that. So the first part is the stars. So here I'm grabbing the original sim, so the MPM simulation directly. I'm not touching the up-res part of the setup. And I'm just decimating this point cloud because I want a smaller subset of points. Then I'm going to assign a color to each of those points. And those colors were just picked from the reference images that I had. I'm also setting a random p-scale. And so those are the points that are being used to do the light instancing. And then the other set of points are the points used for the emission. And yeah, after that, I don't think we have to go through this whole setup. Like in this case, this is just like taking the points and rasterizing them to a volume. And then I'm rendering the VDBs, and I have like a color VDB. And then the last setup is very similar, but it's for the rocks. So I'm just changing the p-scale of the points, adding some orientation, as I said. So very similar to this. So, and again, this is the final shot. So one last thing that I wanted to say. Recently, I've been working on some MPM improvement, and more specifically, I've been working on a deterministic particle-to-grid step of the MPM solver. So as some of you might know, at the moment, this step is not deterministic, so it means that if you run the simulation multiple times, you're going to get like slightly different offsets at the end. So obviously, we want to fix that and get a better output to be able to reproduce bugs or other things. But I realized that by doing that, I was also able to get some speed improvement. So if you look at the bar plot on the right, all of those are the recipe that we have that ships with Houdini. And here you have like the performance increase, not on the whole MPM solver. So this is just for the particle to grid step of the solver. But know that in some cases, this step takes about 75% of the whole computation of the solver. So maybe it's not going to be like 4 times faster, but you can expect like a real speed improvement from this. And at the moment, it's early days, like I'm still testing this, but just to give you a glimpse at what's coming. This is not going to be like something that gets shipped to you very, very late. Like we're trying to backport that to 20.5, so you won't have to pay anything extra, and this speed improvement should be packaged with the current version. Just to let you know that we're actively trying to make things better and faster so you can be as creative as possible. And that's it. Thank you for listening.